Okay, now we have one lecture to cover all the rest of physics. We've been going, the pace, as you notice, has speeded up. The last lecture covered a great deal of material, a lot of it very abstract, most of which I do not ask you to try to reproduce. This is, I won't ask you to write an essay on, on exchange forces or gluons or the color force or anything like that. I'm just giving it to you too fast, so sit back and enjoy it a little bit. Basically speaking, unless I point out something as I want you to know it, the main thing you need to know are the things that are in the textbook on that chapter. There won't be any essay question on advanced quantum mechanics, field theory, exchange particles. I did want to mention the Higgs. And the Higgs is something that's in the news. If you read Herman Wouk's novel, A Hole in Texas, it's all about the discovery of the Higgs. You ask a lot of physicists, if you could make one discovery in the next year, what would you like to discover? They'll say the Higgs. So let me tell you what the Higgs is. The Higgs is a particle, hypothesized. And because it's a particle, it's also a wave. And because it's a wave, you can have a wave at very low frequency. It just becomes a static field called the Higgs field. It's like an electromagnetic field, electric field, magnetic field, Higgs field. And if you shake the field, you get a Higgs wave, and a Higgs wave is a particle wave. So everything is a particle, a wave, and a field. The Higgs field is something special, though, and it was invented for a very peculiar reason, which I think you will enjoy hearing about. We think of magnetism as a form of electricity. When you have a moving charged particle, one of the forces it can exert on other moving charged particles was originally called magnetism, but now we think of it as part of electricity. People used to think that things fell and the planets went in circles, and they didn't realize these are two aspects of the same thing we called gravity. So physicists love it when they take two things that seem to have nothing to do with each other and they describe them as two aspects of the same thing. There is an attempt now, and people are just breathing heavy as they sense it's within their grasp, to come up with a theory of everything. In this theory of everything, the electric field would actually be related to the strong force, and that would be related to the gravity force, and these would all be seen as different aspects of the same force. And that this just makes physicists drool, the idea that they can unify all the forces of physics. They've come pretty close. The strong, weak, and electromagnetic forces have been unified. But in order to do that, they had to make a rather weird assumption. And that's what gave rise to the Higgs. Now, including in gravity is the hope of string theory. And they've come up with a theory, just that it makes lots of predictions that aren't true, and they figure, well, you can adjust that. And so string theory is really out there. But if you want to include what's called quantum chromodynamics, is this theory of strong, weak force, the radioactive force, the electromagnetic force, chromo standing for color. This unified theory has to assume, in order to work, that the electron has zero rest mass. Now that's a problem, right? But it also has to assume the quarks have zero mass. In fact, it has to assume that everything has zero mass, not just the photon. Now that, for some people, that would just be enough to say, well, that theory is wrong, let's try a new one. It turns out you can salvage this in a rather fascinating way. Suppose you postulate that the universe is empty space, has another field in it. This is not the field which waves to make particles. This is a field like an electric field, and it exists everywhere in space. And let's give it a name. We'll name it after the person who proposed it, Mr. Higgs. So assume now that the universe, in addition to having lots of things, could have this huge Higgs field. and exists everywhere in space. And the Higgs field has a certain property. It interacts with particles in a particular way that I could write down. It wouldn't make much sense unless you've studied the math. And with electrons, it interacts just a little bit, and with protons, much more. Now, it turns out you can do this in such a way that these massless particles, particles that have no mass whatsoever, when they exist not in a vacuum, but exist in this field, they behave exactly as they would if they had mass. A little bit like light. Light goes at the speed of light, right? But it slows down when it goes through glass. Well, these massless particles will slow down when they go through the Higgs field. In fact, the math works out that these massless particles will behave exactly as they would if they really had mass. You think that's cheating, but it saves the theory. Because in the early universe, this Higgs field wasn't there. And so every particle was massless. And everything works. The Big Bang works. You can make this all work out. And then at some part of the early universe, the Higgs field changes. It's what's called a phase transition. The Higgs field basically goes from its vacuum value to a lower energy value. Don't worry about understanding this. It's a transition of the vacuum. The Higgs field turns on. It's something that's called spontaneous symmetry breaking. You'll hear these terms. If you read, you're a Scientific American, you'll come across these terms. You will have heard them first here. You don't understand them here, but at least you will have heard them first. When you see them the second time, they'll be a little bit less mysterious. So there's this postulated period. It also corresponds to a period known as the inflationary universe in the early universe, and it causes a sudden expansion of the universe. When this Higgs field turns on, the particles now start behaving as if they had mass. And right now, that field is turned on. And so particles appear to have mass. By the way, it's also possible that this field could change yet again. And if it does change yet again, this is perturbing the vacuum, then every particle would have a different mass, in which case the entire universe would basically explode. People worry about this. There's actually a debate going on right now. When you build a super particle accelerator and you produce energy conditions that didn't exist before, some people worry that this could trigger the change in the vacuum, which would then spread over the universe with the speed of light, and we would all be gone with the speed of light. They worry about this. Actually, my colleague Pete Hutt wrote an important paper on this, pointing out that no matter what accelerator we build, we're not going to make conditions that didn't exist before in the universe. If you look around the universe, look at high energy particles and colliding, you'll find that they all existed elsewhere. So we're not really fiddling with the universe in that fundamental way. If this sounds like science fiction to you, that's okay. You don't have to understand it. This is much more solid than science fiction. Everything I'm telling you is based on an attempt to explain the world as we know it, based on very solid mathematics that has undergone the scrutiny of many people. And it may even be right, but we don't know yet. Inflationary universe has to do with the early universe and how it expands. We'll be talking more about that very soon. We only have an hour left, though, so I'm going to have to hurry. I was asked last time about the Casimir effect, C-A-S-I-M-I-R, and I know what the Casimir effect is, I just couldn't remember. Okay, the Casimir effect, this is an answer to the question about what is the Casimir effect, but it also turns out to be relevant for the universe. It's the following. The universe is space, and I tell you to think of space as a fabric. We call it the vacuum. It used to be called the ether, A-E-T-H-E-R. Now we call it the vacuum. But this vacuum, when it vibrates, is a wave, such as light or an electron, a particle wave. Now, it turns out, if you look at the mathematics of such vibration, that the vacuum can never be completely at rest. According to the current field theories, the vacuum is what's called a harmonic oscillator. And harmonic oscillators never can get zero energy. In any of the possible modes of oscillation, there's always a little bit of energy. That's called the zero-point energy. Now, is the zero-point energy really, I mean, if it's an energy that you can't touch in any way, it's the minimum energy space can have, then what's the big deal? You can't extract it if it's the minimum energy space can have? Well, there is a little bit of a problem. That is, it calculated, it seems to be infinite. Oh, okay, infinite energy everywhere, but you can't extract it. So what's the big deal? Well, Casimir figured out how to extract some. Works as follows. You take two metal plates and put them close to each other. Now, there's lots of energy out here, there's lots of energy out here, and there's lots of energy out here, but it turns out there's a little bit less. The reason there's a little bit less is that the presence of these metal plates restricts the kind of oscillations that can exist in here. They have to be consistent with the presence of those metal plates. And as a result, there's a little bit less energy in here. Oh, well, that means there's more energy out here and less in there. Won't that push the plates together? That's Casimir's prediction. You take two metal plates in a perfect vacuum and put them close to each other, and they'll be attracted. So the experiments have been done. They were very tough because the effect is really tiny. The reason is most of the energy is here. Most of the energy is in here, too. The only ones that are missing are really the oscillations that have really long wavelength. You see, this restricts them to be short wavelength things. So there's just a few things missing. And as a result, the pressure isn't very much. But it's been measured, and it's there, and it agrees with the prediction of the zero-point energy. Wow. Can we extract this energy? Yeah, you can extract it, build plates, put them together. As they come together, you get some energy out. Is this an infinite amount of energy you can extract? Well, you don't get to do it again, right? You build the plates. Nobody, it's a way of getting some energy out, but nobody has figured out any way to come within many orders of magnitude of being able to do it. So it's mostly the science fiction writers who think of extracting the energy from the vacuum. That's the Casimir effect. But the thing about the Casimir effect is it makes you wonder whether or not this zero-point energy is really there. There is a problem. All of energy has a gravitational field. And so you think this would have an infinite gravitational field. The vacuum would have an infinite gravitational field. And that doesn't seem to be there. In fact, there's another issue, which is if you work through the equations of general relativity, the pressure of this thing tends to make the universe expand very rapidly, to accelerate. Now, my former student, Saul Perlmutter, along with other people, there were several experiments going on around the world. Alex Filippenko, who's teaching Astronomy 10 in the fall. If you like this course, take Astronomy 10 in the fall from Alex Filippenko. It was a course that inspired this course. Inspired it because when I looked at his course, it was astronomy at a very, just full of material, very, very intensive course, and yet everybody loves it. Voted the most popular course on campus. Inspired this course. The pressure from this should accelerate the universe, and a few years ago, Saul Perlmutter, who teaches the Physics for Music course once a year. You should take that too if you like music. It's another one of the discovery courses. Alex Filippenko worked on a separate project with the same discovery, so it's been verified. The universe is accelerating. It's expanding more rapidly. We'll talk more about that very shortly. And so maybe this zero-point energy explains it. And so you do the calculation, and you find out how much expansion you get from the zero-point energy and how much expansion you see, and, well, they're not quite in agreement. They differ by a factor of approximately. How many zeros? 120 zeros. 10 to the 120th. That's the disagreement between theory and observation. Some people refer to this as the largest outstanding problem in theoretical physics. My own guess on this is that this zero-point energy is not calculated the right way. We're making assumptions about the vacuum that aren't accurate. Yes, they're good up till now, but when you start looking at very high frequencies, it really doesn't make much sense. And this calculation is just nonsense. We should stop thinking about zero-point energy as being responsible for the acceleration of the universe, but who knows? It's not really my field. That's the Casimir effect. We talked about the Higgs. Just talking about the universe out there, let's get to the Drake equation. Frank Drake's equation has achieved worldwide fame, gotten people really excited about searching for life in the universe. And basically what the Drake's equation says, to put it in its simplest terms, is listen to the numbers. There are 10 billion stars in the Milky Way. There are 100 billion countable galaxies out there if we took the time to count them. Every place we look, we find these galaxies. So that's 10 billion times 100 billion. A billion is, depending on whether you're British or English, a quadrillion. This would be a quintillion. That's a pretty big number. You really think we're alone as the only life in the universe? Okay, so that's the essence of the Drake equation. Now, at this point, Professor Drake, I have to honestly say, you did some marketing, which I consider a cheat. Wrong, let me put it that way. There's something called the Drake's equation that tries to take this expression that I just gave you and make it formal to give it the look of being science. And what he does is the following. It became Drake's equation, really, really famous. Writes down this equation. It's in the book, so you don't have to copy it. And he says the probability of there being life out there depends on a bunch of factors. One, how many stars are out there? So let's put in the number for the number of stars out there. Now you can put in the number of stars in our own galaxy if you want, or you can put a number of stars in the universe if you want, depending on whether you care about there being life in the universe or life only within our own galaxy. Many people are more interested in life in our galaxy because there's some hope that we could communicate with this. I mean, the galaxy is less than, it's 100,000 light years away, apart, and so signals coming from other intelligent life would only take 100,000 years to reach us. And so if they existed 100,000 years ago, I mean, humans have been around for more than 100,000 years. Maybe we can get signals from them. So you put in the number of stars. Now, how many of the stars have planets? We didn't really know this answer. Do most stars have planets? Well, a few years ago, we didn't know. But thanks to some really remarkable work by Jeff Barcy, who is now here at Berkeley, Jeff has been able to show that most stars have planets. And he does this using our old friend, the Doppler shift. Do you remember what the Doppler shift is? You should remember what the Doppler shift is because it's the change in frequency when something is moving towards you or something is moving away from you. That's the Doppler shift. Marcy looks, and he came up with some really sophisticated techniques for looking at the Doppler shift of a star. So here you are looking at the star. Now, as the planet goes around the star, the planet is also pulling on the star, and so the star is pulled a little bit towards the planet in this way and that way. So when a planet goes around the star bobs back and forth a little bit. And he can measure this by looking at the spectral lines of the star and looking at their Doppler shift. And he's gotten very good at this. It's an exceedingly difficult experiment. Certainly worthy of the highest prizes given in science. And it will be honored, so honored sometime in the near future, I would guess. What he's found is that most planets have stars. Now, I mean, most stars have planets. Okay, planets do have stars. What do they have stars on which we could live? Well, this is the fraction here for the number of stars that have planets. You can put in some number. I don't know, put in 50%, put in 1, put in 20%. Doesn't really matter. It's not going to affect the outcome of this equation very much. Now, how many of these can sustain life? You multiply all these things together, and you find that, well, how many of them can sustain life? Jupiter doesn't. Now, let's say life like we know it. You don't want to get too wild here. Let's take ordinary carbon-based life. The reason you want to take ordinary carbon-based life is you work out this equation, and you're going to find it's pretty probable. So let's not worry about exotic life. And how many can sustain life? Oh, who knows? 1 in 10, 1 in 1,000, 1 in a million? Take 1 in a million. Do your best to calculate that number. How many of them will actually have life? If you can sustain life, will life begin? Most scientists believe the odds of that are very high. That life, given the conditions, will start up. Will that life become intelligent life? Because it's not going to be worth communicating with if it's just a bunch of bacteria. So, how inevitable is intelligent life? Really interesting question. You got to think about this and debate this. And some people will say it's not very likely at all. Other people say, well, intelligence is like a programmable computer. It's more flexible. If you have intelligence, you can adapt to changing environments. Well, maybe you needed changing environments. A wonderful book called Rare Earth by Peter Ward and Don Brownlee, which talks about this issue of the Earth, what conditions on the Earth were necessary in order to have intelligent life, as opposed to a planet filled with bacteria. And they work out some numbers there. Secondly, if it's intelligent, does it want to communicate? Well, that's a good question. Here we are listening, some friends of mine are listening to signals from space, hoping to pick up this communication, but we're not sending anything. Well, it turns out we are sending something. Old episodes of I Love Lucy and so on are going out because television signals go out. But we're not sending them with very high power. You really have to send things with pretty high power if they're going to be picked up by distant stars. So at some point you have to say, what's the probability that a civilized life will say, there may be someone out there, and gee, we have learned how to live in peace. It wasn't easy, but we'd like to share this. So let's send out some signals to tell people how to do this so they won't destroy themselves with a nuclear war or a biological war as we almost did. So what's the probability there? 1 in 10, 1 in 1,000, 1 in a million? Put in some numbers. And then finally, do you really survive? I mean, do we destroy ourselves? Technological civilization, the Mayans destroyed themselves. They disappeared. They were rather highly advanced. They had learned how to live in the jungle in ways that we still don't understand today. And then they vanished, probably because they got involved in a kind of wars that they couldn't sustain, destroyed their infrastructure. Arthur Demarest gives a wonderful lecture on this. And as a result, they basically collapsed. We depend so highly. I mean, if the grocery store stopped having food, where would you get it? This infrastructure is so important to us all. And so you have to put in the probability of surviving. Now, most people put some numbers into these equations, the ones that they don't know, they make up a plausible number. And because this number at the front is so huge, they find it is highly probable that there will be life out there. Now, Ward and Brownlee look at it a little bit more carefully, and they look at, can sustain life? Will it be intelligent? What is this one here? Interesting. What is the probability that life would occur? Is it 100% like most people think? Well, have they really thought about it? If you ask a scientist what's his opinion, they'll give their opinion. But did they really put their scientific expertise behind coming up with that number? Usually not. Beware of scientists who think they're smart. This is a danger. A scientist who has done things, discovered things, now thinks he's smart. You'll find the same thing among real estate developers. Choose 10,000 real estate developers, and 9,999 of them will basically do okay, and one of them will become a billionaire. Is that a fluke? Is that because 1 out of 10,000 is going to be really lucky? There's pretty good evidence that that is working. Given that, does that mean he's much smarter than everybody else? Not if that's the mechanism. Will he think he's much smarter than everybody else? Yes, he's the billionaire. Same thing's true among science. You wind up doing things in science. You discover something that nobody ever knew before. Suddenly you think you're a genius. Right? And then you start spouting off opinions on things you haven't thought through and applied that same scientific care. The most important aspect of the scientific method is the self-skepticism, the being cautious, the can I be wrong step, which you do over and over and over again because you don't want to publish anything wrong. So let's take a look at this thing. How many people have really thought about this thing? Could this number be, what is it, 1 in 10? That's what most of my friends say. Could it be 10 to the minus 50? No, how could it be so small? Life? Well, you know, the thing is, we don't know how life began. We really don't. Was it an RNA that somehow spontaneously got together? Was it a bunch of proteins? If you get some lightning and thunder going, you create some proteins, but do they form themselves into amino acids? Do these amino acids ever become something that can reproduce itself? What's going on here? Is it ancient prions or something like that? You know, the fact is, we really don't know how life began. And given the fact that we don't know how life began, what evidence do we have that it's highly probable? I talked to my friends about this. I remember a conversation with Barney Oliver. He said, well, but life started so soon on the Earth, so it must be probable. And this is the answer they'll usually give you. Since we have it here on Earth, it must be very probable. Let me give the other answer. Let me say the probability is 10 to the minus 25 or something like that, really tiny. But enough so that Drake's equation says that n turns out to be 1. Or maybe 1/10. There's 1/10 of a chance of getting intelligent life in the universe. And it happened here on Earth. So we are the ones. Is that possible? Well, the fact that we're here discussing it, we're the only ones who would be discussing it. Is the universe consistent with this model? Yes, it is, because it says there'll only be one in the universe, and the one in the universe who happens to be that one will be the one that discusses it. Put another way, Drake's equation has such large unknowns in it that you cannot rationally use it in any scientific way to make any prediction about whether or not there's life in the universe. Now, as I've told you many times in this class, there are certain aspects of relativity theory that I don't spend my time working on because my intuition tells me they're not right, and that's because I believe in my own free will. That's not a scientific statement. I sense I have free will. I think it's not an illusion. And so I'm not going to waste my time in theories of science that deny that, such as wormholes and such. But I could be wrong on that. Maybe my free will is an illusion. We have to make decisions what we work on, and they're not always based on science. They're based on some sort of intuition or maybe a desire to have free will. Well, there are people who believe, regardless of the uncertainty in many of these things, come on, there's got to be life out there. Let's listen. And that gives rise to Project SETI. Search for Extraterrestrial Intelligence. SETI. You should know those acronyms. Search, it's in the book, for extraterrestrial, meaning not on the Earth, could be on the moon, intelligence, because that's what we're really interested in. Search for extraterrestrial life is less interesting. These people are listening to the signals coming from space, hoping that someone out there, according to the Drake equation, with a few terms fudged, tells them they're likely to find something. There's another way to justify this. The odds of finding something are pretty small, but if they do find it, it will be one of the most astonishing discoveries ever. It will put Columbus to shame. You know, this is the greatest discovery ever. And so even though the odds are small, it's worth going for. And besides, if you enjoy the technology, why not? And the government doesn't like to fund this project. It's too far out. But it's the sort of thing that you can stir people's imagination and get private funding, and a lot of it is privately funded. So that's Project SETI. And enough of that. Let me go into the origins of our universe, the Big Bang. How we got here. I mentioned I want to see how well this works. I'm not sure how well it will work. So let me see if I can superimpose these things and it comes across reasonably well. I think this works pretty well, so I'm going to try this. Okay. So this first slide here is meant to represent the galaxies in the universe. Now, they're not neatly arrayed in a rectangular array like that. They're kind of scattered, and they're in clusters and so on. But ignore that for a moment. I put them so neatly here so I can share a concept with you. So pretend for the moment that we're looking at a region of space where they are neatly arrayed like this. Just by chance, there's enough of them out there, you'll find some region like this. Now, Hubble's discovery is that this is not a static condition. It's changing with time. That was what now has been called Hubble's law. And I'm going to change the color, but that's not what's changing. I mean, in fact, that's not what I want you to notice. It's just that the second one has a different color. But just so you keep the first one and the second one straight. So notice the change. Okay? A little bit hard to say. Let me put them on top of each other. And here you can notice the change. They're moving. That's like, I talk about a raisin bread analogy. They're the raisins in the bread. Those are the galaxies. They're the raisins in the bread. That's the galaxy. They're moving apart from each other. And if you put them on top of each other, and let's say we're the one in the middle, then look at that. They're all moving away from us, aren't they? In fact, I sketched this up here. Here are the arrows. And you can see they're all moving away from us. Gee, we must be in the center. No. This is the most, you will wind up in your lifetime, people, if they hear you took a physics course, people will say, well, what's this about the expansion of the universe? How come we're at the center? Isn't that peculiar? No, we're not at the center. Let me show you that. Suppose we happen to be sitting on another galaxy, like this one here. Let's say that's Andromeda. If we're sitting on Andromeda, then by definition, you say, well, let's measure everything with respect to our galaxy. So let's make Andromeda be the one that's not moving. There. Now Andromeda is not the one that's not moving, right? And now look at all the other galaxies. There's the Milky Way moving away from us. And from us on Andromeda. And here we have the relative velocities of all the galaxies. And it looks like everything's moving away from us. Oh, suppose you go to, I don't know, some other galaxy, M97. That's up here. There's M97. You're sitting on that one. Then by definition, that's the one that you measure everything with respect to. And if you do that, sure enough, everything seems to be moving away from you. Basically, everything's just getting bigger. And that's the expansion of the universe. There's nobody at the center. You get a multiple choice question on the final exam saying, does Hubble's law prove we're at the center? The answer is no. It just shows the whole universe is expanding. Now, a lot of people are bothered by this. They say, what is it expanding into? The current best guess, based on the measurements we've made, is that the universe goes on forever. But if it goes on forever, how can it get bigger? Well, we're getting in here into issues of infinity, and quite frankly, infinity is something you've got to get a little bit used to thinking about. Let me give you a little infinity puzzle. I'm going to give you two lists of numbers. 0, 2, 4, 6, 8, 10, 12, 14. They're basically the list of all the even numbers, including 0. How many are there? Well, there are an infinite number of them, right? So there's an infinite list. Let me give you another list of numbers. 0, 1, 2, 3, 4, 5, 6, 7, go on forever. How many of those are there? They're going forever. Infinite. Well, which has more? Interesting issue in mathematics. If you try to come up with a way of answering this consistently in a reasonable way, what the mathematicians finally realized is if you can put them in what's called a one-to-one correspondence. I mean, if you have red beads and green beads and you can't count above 10, you can still line them up. And if they line up and they line up perfectly in a one-to-one correspondence, we say it's the same number. In the same way, we say this has the same number of things as this does. A subset of infinity is still infinity. More math than you were expecting to get today, right? I'm not going to quiz you on this. Let's take another example. Suppose we have a rubber band that's infinitely long and has these little things on it. Call them galaxies. And there are an infinite number of them. Now suppose we stretch this. Then we get a rubber band that looks like this. How many galaxies are there? Well, actually, this looks like the even numbers, and this looks like the odd numbers, but it's the same number of galaxies. It's just stretched out. Well, where did it go? It turns out there's lots of room at infinity. So the universe can be expanding because if it's infinite, it's expanding, and there's no problem. It's just everything is getting further apart, but it still fits in infinity. So this is the current view of the universe. Now, there was a view a few years ago that maybe the universe is finite. And I don't have to discuss that anymore because now the measurements indicate it's not. And then you could ask, if it's finite, how can it go on forever? Well, it doesn't. It's finite. And it's like that story I told you about walking to the end of the room and coming back the other way. It's like the Earth being finite. But I don't want to go into that because these days the universe does appear to be infinite. And it seems to be expanding. I started a project, early 1980s, to measure this expansion and to watch how, as it's expanding, it would slow down. Why do you expect it to slow down? The reason is all the mutual gravity. These things are moving apart. Why are they moving apart? That's the Big Bang. I'll get to that in just a moment. But as they're moving apart, their mutual gravity should slow them down. This would be the deceleration parameter. How do you measure that? You have to look at some really distant things. So I started up a supernova program to look at distant supernovas. And looking at these distant supernovas, you would measure their velocity from their Doppler shift. You'd measure their distance by how bright they were. And then you could see if they were slowing down. Well, I had a problem with that project. It wasn't that I couldn't do it myself. It's that I had a student who was solving all the problems much faster than I was. His name was Saul Perlmutter. So he took over the project. I dropped out to work on other things. He worked at that for another 5, 7 years, solving problem after problem after problem, trying to figure out how to make this thing work. He finally solved them. Another group joined in. And they actually succeeded in making the measurement to detect the gravitational slowdown of these things mutually attracting each other. There's only one problem. They got the wrong sign. Things weren't slowing down. They were speeding up. How can that be? What about the gravity? Well, the gravity should slow them down. Why are they speeding up? This, immediately, the theorists came back to the old zero-point energy. That would speed things up, but if you do the calculation, it speeds them up too much. So all they have to do is sort of tone down the zero-point energy by 10 to the 120, which they haven't succeeded in doing yet. So this is another truly outstanding issue. How can we understand this expansion? It's given a name. I want you to know the name. This effect discovered by Perlmutter, who's teaching the physics of music. He's doing it now. He's going to do it again a year from now. It's a discovery course. Saul Perlmutter, and done by others, including Alice Filipinko in an independent study. This expansion is referred to as the dark energy. Now remember, I already talked about the dark matter. Don't get those confused. The dark matter is this matter whose identity may be WIMPs, maybe machos, maybe something else. We know it's there because of the gravity it causes that holds together clusters of galaxies, helps hold together the galaxy itself. That's the dark matter. We thought there'd be lots of dark matter and that would slow down the universe, but there's something that's even stronger called the dark energy. And the dark energy is causing the expansion of the universe to accelerate. And what is the dark energy? Maybe it's zero-point energy, but if it is, it's sort of surprising to be off by such a big factor of 10 to the 120th. Maybe it's some force we just haven't thought about yet, something we haven't detected, because it's a very weak force, but it's felt only at very large distances. Maybe there's something that, maybe the vacuum itself repels itself in some way that makes the universe accelerate. Once it gets bigger, Then there's more of that stuff to repel it, and so it accelerates even more. The early universe, well, gets bigger. It was always infinite. But as things get apart, the amount of vacuum energy increases. So that's called the dark energy. The dark energy is to account for the acceleration of the universe, the fact that not only are these things flying apart, but their velocity is not even slowing down as you would expect. It's actually accelerating. And gravity shouldn't do that. Sometimes you'll see this referred to in the newspapers as anti-gravity. And they'll refer to it that way. Why? Because they want to grab your attention. They want you to read the article. And so you think about, oh, I don't know, Star Wars with a little spaceship that hovers using anti-gravity so it doesn't, you know. This isn't that kind of anti-gravity. This doesn't even seem to be a repulsion of masses. It seems to be a nature of space itself. But since it is a repulsion, and it actually fits into general relativity theory, that sometimes people call it anti-gravity. But let's ask the other question now. This is the one that Gamow asked, sort of a silly question. If things are flying apart, suppose we go backwards in time. Ask when would all these galaxies be on top of each other? And now if you do the measurement, we know the number fairly well. It's 14 billion years ago. 14 billion years ago, all those other galaxies would have been right here. Now, that couldn't be, right? That's not a real possible situation, right? Well, Gamow was the first person to say, let's think the unthinkable. Let's ask, could that have been the case? Could everything have been here? It would have been very dense. It would have been like the whole universe was the inside of a star. I don't mean a region of the universe. I mean the whole universe, because cosmological principle, everything out there is just like it is here. Everything was compressed. There's a lot of stuff coming in from infinity. And so you could fill up the entire universe with galaxies all on top of each other. It becomes infinitely dense. What would that be like? It would be like the inside of a star. Now, Gamow had the intuition to think this through. He thought this was a reasonable thing to do. If I had been alive at that time, I think I would have assumed he was wasting his time. But he thought it through, and he said everything will be so hot, it'll be like the interior of a star. In the star, we know that fusion is taking place. Right now, we're building helium out of hydrogen. He said, as I look around the universe, you would expect there to be, well, about 10% of all the nuclei are helium. 90% are hydrogen. And then there are a few other things like carbon and iron that make life interesting for us. But if you look in stars, it's mostly hydrogen and helium. Why is the universe 10% helium? Why is that? And his reaction was, maybe it was all created in the early universe when the universe was so dense it was like the inside of a star. In the inside of a star, you'll get fusion. Maybe because it's expanding so rapidly, it only lasted for a few minutes. And in those few minutes, the whole universe was the inside of a star, and the hydrogen that was there became helium because of fusion. And then the thing expanded and it cooled off because, remember the fire extinguisher? Things that expand, cool off. Refrigerator pumps, they expand, they cool off. The universe cooled off. At that point, the fusion stopped, and that's why we are 10% helium instead of 100% helium. And he said, let me work this through. I mean, really ridiculous thing to do, right? What a ridiculous theory. This is now the standard theory that is called the Big Bang, accepted by everybody working in the field, just about. There are some people who don't accept it, but they don't really, they haven't been able to predict anything, whereas this theory has been able to predict a whole bunch of things. I'll show you the most important in a moment. So this is the picture, that the universe was once everywhere dense and hot, and fusion took place. And maybe even earlier than the helium, maybe this is where protons came from. Maybe in the early universe just had quarks. In fact, maybe there was just energy. Maybe it was just really hot energy. And the photons in pair collisions produced quarks. And then these quarks became protons as everything cooled off. This is the standard picture of the Big Bang that, as I say, is no longer in dispute. If you believe in divine creation, I have no problem with that. This is the way God chose to do it. And here we have this universe that is now the helium was made, but let's go back to that early universe. Let's look at it. Now imagine, there's no edge to this. It's everywhere. The whole universe is just full of hot stuff. It's the inside of the sun. There it is. That's my picture of it. Okay, you have atoms, a few of them. Those are the dark spots. You have electrons. Those are the red spots. You have protons. Those are the blue spots. You've got lots of photons scattering all over the place. You've got quarks and gluons and everything else. It's a big soup. Gamow used a Yiddish word called Elam, which means soup. And the universe was full of this. There was no space anywhere. What happened before this? I mean, it was really hot. Did it become infinitely hot? Well, we actually don't have the physics or the math to be able to figure out what happened when it gets to infinity, when everything was infinitely dense. We really don't know. We can talk about 1 minute after the Big Bang. We can talk about a millionth of a second after the Big Bang. If you get to the Big Bang itself, then we really don't know what's going on. At this point, physicists like to speculate. My favorite speculation, and this is sheer fun, is that the universe didn't exist before the Big Bang. That the Big Bang was the creation of the universe in the first place. Well, what existed before that? Well, nothing that we are familiar with. No matter, because matter is a wave within the vacuum of the universe. Maybe the vacuum of the universe didn't exist. So there's nothing that we know of that we can talk about existing. But it could have started in this state, this very energetic state, 14 billion years ago. And it was started in such a way that the energy was so great that it expanded and exploded and became less dense. When it got to the point where protons could exist without being broken apart by the heat, then we had protons and electrons. And then it got to the point where helium could exist without being broken apart. That occurred 3 or 4 minutes into the Big Bang, after the beginning. What happened before the beginning? Well, space didn't exist. So we can't really talk about it. In fact, even more fun, if you want to speculate along these ways, is to say in the theory of relativity, events are specified by space and time. So what happened to the time before space existed? And here I'd like to have some fun. This isn't solid science. This is what a scientist does when he tries to use the knowledge he has and think about it in a coherent way. This is what Gamow was doing when he came up with the Big Bang. But the Big Bang, it turned out, is verified, as I'll show you in a moment. So what is my speculation? It's a speculation shared by other physicists too. Time didn't exist. Time, this mysterious thing that we don't really understand, that paces us. We have a sense of time that's probably based on our size and the rate at which we can develop new thoughts based on our physical size and the rate at which nerve pulses go. But time does seem to progress. There's this concept called now that doesn't appear in physics, but you know what I mean by it, now. Except when I said that word was a while ago. That was 10 seconds ago. So this mysterious thing, time, maybe it didn't exist until the universe was created. Maybe space and time were created. Speculation, but it's a sort of fun speculation. Can I make a prediction out of that? No. Therefore, it's not really science. But it's fun speculation. Could there be another kind of time that existed before that, and the time that we know about, which exists only in our own universe, was created? Okay, enough of that wild speculation. Let's get back to things we know. Here's the early universe. There's good reason to think the universe was this way. And let me now follow on with what Bob Dicke and Peebles did, for which they should have gotten Nobel Prizes. Wilkinson, 2 of them have passed away now. They should still give Peebles a prize for this. Okay, what happens, as this thing is expanding, it's cooling off. As it's cooling off, every now and then an electron and a proton will come together to form a hydrogen atom, but as it gets cool, that hydrogen atom is less likely to be broken up. So let me get rid of the electrons, which are red, and the protons, which are blue. Just pull them away. And we're left with only hydrogen atoms. It's less dense because it's somewhat expanded here. Oh, let's see, I left something here by mistake. Okay, there it is. And here are these photons. Now, the photons are bouncing around. You notice that, how they bounce off each other? They bounce actually off the atoms. Actually, they bounce off the electrons, so they shouldn't be bouncing anymore because the electrons are gone. And so what happens is at this moment, which actually took place about 500,000 years after the Big Bang, the photons stop bouncing. It's as if the universe goes from being milky to suddenly as clear as water, because the light doesn't bounce anymore. So let me get rid of the bouncing photons. Since these things, let's get rid of the atoms so they won't get in your way. And let's get rid of the bouncing photons and leave only photons going in a straight line. So this is the milky, this is sometimes called the decoupling moment. It's about 500,000 years after the Big Bang. And at this point, this light is all moving in more or less straight lines. Well, it might hit a galaxy. Galaxies haven't formed yet. Later in this time, as the universe is expanding, the mass of the atoms, these things are removed. They don't, what did I do with them? These things, they're still there. But they begin attracting each other and clumping. And they begin to form stars. When that happens, here we have something which has these photons, but it's going to turn out that these are microwave photons. So you don't see them. When the clumping things come together and they form stars, then they start emitting visible light again. And this is an exciting time in the universe in terms of the history, because here you have this Big Bang when everything was hot and bright everywhere, furiously hot and bright, and then it cools off. You get the decoupling, so at that point the microwave photons just travel in straight lines. But you still have these little atoms around. They begin to feel each other's gravity, and they begin to clump together. They got lots of time. They got 1 billion years here, more. This is happening about 1 billion years after the Big Bang. They start forming stars and clusters of stars that become galaxies, and they start clumping up like this. And people do computer simulations these days to see how this works. And it looks reasonable that the gravity caused this uniform matter to start clumping up. By the way, these photons were originally really hot. But if you look around here, let's look at the photons that are traveling towards where we are, okay? Let's find one here. Let's say we're here in the middle. And here's one that's moving towards us. And let's say it'll take, I don't know, 14 billion years to get there, because it's far away. So here it comes in 14 billion years. And here's another one, about 14 billion years away. Light years away, it's going to reach us. So we can find these ones that are going to reach us. Just the ones that are going past us, ignore them. Let's just look at the ones that we are going to see today. And not only that, but there's some that are further away, like this one. That'll reach us in 28 billion years. So it's halfway there today, and will get to us 14 billion years in the future. So look at those two. Ignore everything else. In fact, you have a great brain. And if you stare at this long enough and you concentrate on the ones that are aiming right at us, your mind will be able to ignore all the others. So just try that. And most of you have succeeded. Here are the ones that are reaching us today. Here are the ones that will be reaching us in another 14 billion years. Now, here's the key. These photons are visible photons. They are hot. They were from the inside of a sun-like material. However, this ring of stuff is expanding away at very high speed. And as a result, there's a Doppler shift. This was moving so fast that they're visible photons in their own co-moving frame. But because that stuff is moving, wake them up. Whoa. Her? Could someone wake up? Yeah. You're not going to get this from the book. It's too hard. You've got to follow the diagrams. Anybody else asleep? Don't miss this. Okay. So this matter is moving away so rapidly that in its co-moving frame, it's really hot light. But here I am, visible light. I'm very high frequency, but I'm moving away from you so fast that it comes very low frequency to you. It gets Doppler shifted from being visible, hot light, to being microwaves. So when this stuff finally reaches us today, it's microwaves. This stuff will be even lower frequency when it reaches us, because that stuff, being by the Hubble law, was moving away even faster. This stuff is reaching us today. Now, if we look up in the sky and look at microwaves and look up, according to the Big Bang Theory, you expect to see this. This is what Dickey and Hubble and Peebles predicted. And so they started doing an experiment, because Dickey was an experimenter as well as a theorist. And they started looking for this thing, and then I think it was Peebles who went to a seminar being given by Arno Penzias of Bell Labs, and they had been measuring microwaves in the sky, and they found no matter where they looked, they found the same number of microwaves every place up in the sky. And people said, I think you just discovered the Big Bang. And sure enough, Penzias and Wilson got the Nobel Prize. I thought Peebles should have shared in that, and Dickey, but anyway. They found these predicted photons. And they were just what you would expect from the theory of Gamow. This was the great discovery that really showed the Big Bang Theory was the right theory. There have been lots since then, but this was the key. When I was a graduate student, actually I guess I graduated, got my PhD, was working here at LBL. I read a book by Peebles in which he talked about this thing and how impossible it was to see any variation. Now, you expected some variation. It shouldn't be the same from all directions. And the reason was, at the moment of the decoupling, 500,000 years after the Big Bang, the matter had already begun to clump a bit. And so you expect to see a variation. But in addition, the Earth isn't at rest. The Earth is moving, because the galaxy, the Milky Way galaxy, is moving. So you should see a slightly different Doppler shift there than behind you. And I knew enough about experimental science that it seemed to me like a really good project to try to detect the motion of the Earth and see the variation that you'd get from the early clumping. So I began a project to do this. Got a colleague, George Smoot, to work with me on this project. Had several students working on this, Mark Gorenstein. And we began looking for this effect. We wound up flying it in a U-2 airplane. It's a great story. I wrote a book about it. Well, I wrote several chapters of a book about it. We wound up detecting the variation that was expected. We could see the fact that the Earth was moving because this Doppler shift was different from that Doppler shift. A subsequent measurement done by Smoot made a really, really nice plot of this. This is the map of the sky that we got based on this measurement. And so the hot part here is the region that we're traveling towards. The blue part, this is a map of the sky, is the part we're moving away from. And so this is what we call the cosine anisotropy. And this was my project. This was actually exciting enough result that I was offered a faculty position here at Berkeley. And I've been here ever since, based on this discovery. So, nice discovery to make. George continued the experiment to try to see if he could see the little variations that would occur because of the clumping. And he, in fact, with a project called COBE, was the first to see these. And let me show you his plot here. This is I regard this as a really exciting, spectacular plot. Now, he's taken away the cosine effect, which we understand. But here we see the clumping that's beginning to take place as an indication of galaxy clusters beginning to form even in this early moment, 500,000 years after the Big Bang. And subsequent measurements have verified this and gone into much more detail. And now this is a whole industry in physics of looking at these microwaves that are coming from space in order to figure out what was going on 500,000 years after the Big Bang. And the whole thing is fitting together in a nice way. There's still things we don't understand. We don't understand the Higgs field. We don't understand. We don't understand what the dark matter is. There are some issues of how galaxies actually form, the role of the black hole in the center of the galaxies. A lot of questions, but we are seeing this sort of Big Bang behavior. So the Big Bang is no longer in serious dispute. There are some people who say, oh, I don't believe it, and I think maybe it's a continuous universe. But the fact is the Big Bang theory has time and time again been able to either predict the surprises that came along, as in the microwave background radiation, or been able to accommodate them in a very easy way, and none of the other theories do. And based on this, the people who are seriously working in this field, almost all of them, there are issues about the Big Bang, about What happened in the very beginning? Most people now believe there was a period called inflation when the universe was expanding very rapidly. That's not proven yet, and Alan Guth, who first proposed that, will earn his prize if it's ever verified. Right now, it's about the only theory we have, and that doesn't make it right. So that's the picture. So just in summary, okay, you go back 14 billion years ago, and maybe time began, maybe space began, who knows? But it was very hot, very dense. There were quarks and electrons and things, and these, as the universe expanded, it cooled off, and they began to form atoms. And as it expanded even more, it cooled even more. Eventually, you formed stars, and things got bright again. Then you formed galaxies. And we're in such a galaxy. And somewhere within this galaxy, there was a star. In this star, there was fusion taking place. Remember, these stars are all just hydrogen and helium, because helium was made in the Big Bang too. But that's it, hydrogen and helium, almost nothing else. So where did we come from with all of our carbon? Well, there was a star in the Milky Way galaxy that lasted for a long time, and fusion took place inside of that star. And carbon was made. 4 heliums came together and made a carbon atom. 3 heliums came together to make a carbon atom. Okay, so this took place inside of a star. So we had carbon, we had oxygen, we had iron inside of a star. It's a lousy place to live. It's kind of hot. But that star exploded. What we call a supernova explosion. Didn't talk much about the physics of supernovas, another thing future presidents don't need to know. But that star exploded and spewed this material out into space. Now we had carbon and oxygen and iron, as well as helium and hydrogen in space. Now, a second gravitational clumping took place. This all came together and formed another star. It's a star we call the sun. Some of the debris that didn't quite form to that star kept on orbiting it. This is what we call the planets. On one of these planets, which we now call the Earth, there wasn't enough gravity to really hold much of the hydrogen, except for the hydrogen that combined with the oxygen to make water vapor, combined with the silicon to make silicates. Well, that's the oxygen, sorry. The hydrogen, most of it escaped from the Earth. Didn't escape from Jupiter, didn't escape from the other big planets, didn't escape from the sun, but escaped from the Earth. So we are mostly just the interesting elements. We are, carbon, oxygen, nitrogen, some combined hydrogen in the form of water, hydrocarbons, interesting things. But we are the ashes of a star that exploded. Okay, I'm going to wind up a little bit early today, in case people need to see me after class. I'm going to wind up by reminding you there's a review session tomorrow, by reading you a poem. So this is in the book. But I'm going to say everything I just told you, but say it again. This all came about one day when I was reading the Bible to my daughter, and she said, "Daddy, is that what really happened, or is that a fairy tale?" And I said, "Well, this is what people used to think happened. What really happened?" So I started telling it to her. I wound up turning it into a poem. Here's the poem. It's called The Creation. I'm going to repeat to you what I just said. This will take about 3 or 4 minutes, so you can leave if you don't like poetry, I guess. But it's my attempt to describe what I just said to you, what I just taught you in today's class, in a little nicer words. So it's called The Creation. It's a scientist's myth. The creation. Okay. At first, there was nothing. No earth, no sun, no space, no time. Nothing. A new version of nothing. No space, no time. Time began and the vacuum exploded, erupted from nothing, filled with fire everywhere, furiously hot and bright. This is the Big Bang. Fast as light, space grew, and the firestorm grew weaker. It's cooling off because it's expanding. Crystals appear, droplets of the very first matter, strange matter, fragile bits, a billionth of the universe, overwhelmed in turbulence. Of no importance, they seem, as they wait for the violence to subside. Things are cooling. The universe cooled, and the crystals, these little first particles, shattered and shattered again and again and again until they could shatter no more. Fragments, electrons, gluons, quarks, grasped at each other but were burned back apart. The atoms couldn't last when it was really hot. Burned back apart by the blue-white heat, still far too hot for atoms to endure. Space grew, and the fire diminished. To white, to red, to infrared, as you're cooling, temperature goes down, to darkness. A million-year holocaust had passed. Particles huddle in the cold and bind themselves into atoms. Hydrogen, helium, simple atoms, from which all else is made. Drawn by gravity, the atoms gather and divide and form clouds of all sizes, stars and galaxies of stars, clusters of galaxies. In the voids, there's empty space for the first time. We're not only forming clusters, we're also emptying out the space in between. In a small star cloud, a clump of cool matter compresses and heats and ignites, and once again there is light. It's the formation of the first stars. Deep within a star, nuclei are fuel and food, burning and cooking for billions of years, fusing into carbon and oxygen and iron, matter of life and intelligence, born slowly, buried, trapped deep within a star. Now we get to the supernova. Burned and burdened, a giant star's heart collapses, convulses, a flash. In seconds, energy from gravity, that's the source of energy in a supernova, it's gravitational energy, thrown out, overheats, explodes, ejects the shell from the star. The core of the star probably becomes a black hole, but the shell of the star is ejected. Supernova, growing brighter than 1,000 stars, still brighter, brighter than 1,000,000 stars, 1,000,000,000 stars, brighter than a galaxy of stars. That's why we can see them at such great distances. Cinders of carbon, oxygen, iron expelled into space. Escape, free, they cool and harden into dust, the ashes of a star and the substance of life. In Milky Way galaxy, at the edge of Virgo cluster, named 5 billion years later for a mother, the dust divides and gathers and begins to form a new star. Nearby, a smudge of dust begins to form a planet. The young sun compresses and heats and ignites and warms the infant Earth. That's my story of the universe. You are a great class. Thank you very much.